So we are finally at the position, having faffed about with parametrics for a while, we're now able to talk about differentiating parametric functions. Okay? So we are, we're in a position, aren't we, where anything written as y equals, we can differentiate. Sorry, y equals something to do with x. We can differentiate. We call that differentiating with respect to x. That phrase crops up in the homework, which is due on Friday. Did I say Friday or Thursday? I forget. Friday. And we can also differentiate things that are written x is something to do with y, because what we do is we say, right, that gives us dx by dy, and then we just know we flip it to get dy by dx. So we just flip it over, and that gives us dy by dx. And it's dy by dx that we need in order to find the gradient. Dx by dy doesn't give us the gradient. But what we're now dealing with is a situation where we've got separate x and y statements with a third variable in the mix. I'm just making something up here. So how do we find dy by dx with these situations? Well, it's a really simple process which I will try and justify to you. I'm going to try and justify it to you by using a separate example. Okay? So as a completely separate example, I should have done this on the smart book, but it hasn't started up. Can I just get you to differentiate that for me, using the bracket method that we did recently? So this is a sort of just a random example to lead me into the justification for how parametric differentiation works. So just differentiate that using that method that I'm hoping you're familiar with. If you're not, then you know there's lots of practice on OneNote. So I'm hoping that you multiply by the power, you reduce the power by 1, and then you multiply by what you get when you differentiate the bracket, which in this case is just 3. So we end up with 15 lots of that bracket to the power of 4. And we can do that, we should be able to do that. But you may remember that the reason that works is this thing called the chain rule, which I don't tend to talk about because I think it's an unnecessary complication. But what the chain rule says is that what we've actually got there is something to the power of 5, and that something in this case is 3x plus 5. And differentiating that would give us dy by du. And differentiating that gives us du by dx. And so dy by dx, which is what we want, is that dy by du multiplied by du by dx, because what happens when you multiply all that out is the du's cancel and you end up with dy by dx. Now we don't have to bother about that. There's no need to worry about that at all if you can do this. But this is just the justification in particular for why we do that last bit and then multiply by what you get when you differentiate the brackets. And of course if it's a log, then it's 1 over the thing in the brackets multiplied by what you get when you differentiate the brackets. And if it's an e, then it's the same power multiplied by what you get when you differentiate the power. So that thing crops up again and again. It's just that chain rule. So what we do when we come to parametrics is something a little bit similar. So we've got x is equal to something to do with t, and I can differentiate that, and that's going to give me dx by dt. I've differentiated my x equals statement with respect to t, so we call that dx by dt, how x is changing with respect to t. I've got a y equals something to do with t function, and I can differentiate that. That's going to give me dy by dt. What I actually want is this formula for the gradient, dy by dx. And using a similar process to the justification of the chain rule, I can get that if I take dy by dt and multiply it by, well, not dx by dt, but that flipped over, the reciprocal of that, 1 over that, or if it's a fraction, the fraction flipped. Because what happens there is the dt's cancel out and you end up with dy by dx. Some textbooks write it slightly differently. They'll say dy by dx is dy by dt divided by dx by dt. But I hope you can see those two things are the same, because if I want to divide by a fraction, that's the same as multiplying by that fraction flipped. I prefer this method. This method is exactly the same, and sometimes that works better and sometimes that's better. To start with, you'll think, why aren't you showing me that? But as we get into harder examples next lesson, you'll see maybe why I'm choosing to write it that way. But these are the same thing. So let's use this example. I can work out dy by dx by firstly differentiating that. T is the variable, so I multiply by the power, reduce the power by 1, and just like x becomes 1, t becomes 1 when t is the variable. I can differentiate this. And therefore dy by dx is that multiplied by 1 over that. And if you think of it like that, and of course the alternative method is probably easier in this case, but I actually always do it that way. So this is my formula for the gradient. Now there's a difference between what we normally get when we differentiate a function like this. When we differentiate a function like this, we normally get an expression in terms of x, and it then says, okay, find the equation of the tangent when x is 3, or find the coordinates of the turning points. Well, what we've got now is a value of t that we need. So sometimes questions will give you the value of t, sometimes they will give you coordinates, and you have to use the x and y equations to work out a value of t. But differentiating parametric functions will always give you an expression in terms of t. So let's do a bit of practice. We'll start with some basic practice, and then we'll get into some sort of meaty examples. Now, in my online textbook, this is page 251. I have a feeling in the paper textbook, it's 252, I don't know. It's 251 in my online version. Yeah, it's 252. It is 252, isn't it? Yeah. So it's the same questions. We're not going to do all of this, obviously, that would be too much. So can I propose that you all have a go at this one, and have a go at this one, where I hope you're going to rewrite that as 2t to the minus 1 before you differentiate. We're then going to have a go at that one, which throws a little bit of an extra complication into the mix. Yes.
Mine's, I've got a year one
Oh, Josh.
book thing on the wall.
How has that happened? What a mistake
I'm
to
not
make.
sure. Sorry.
Liz, you won't be still ready, so you That's the stats and mechanics book that I bought for you to have at home. I refer to it in the mechanics videos that I've started doing, but it also might be helpful for revising in general. So it was you and Beth. Who was the third person who wasn't here yesterday? Well, yesterday. Who was it? Just make sure you write x as 2t to the minus 1 in E. Yes. Oh. Thank you. Sorry. Remember, 1 less than minus 1 when you reduce the power is minus 2. So this is where I feel like my method of doing it works a little bit better, because I need to multiply that 6t by 1 over that, and if I rewrite that back in terms of in index form, sorry, in normal form, it's easy to flip it. So I end up with 6t cubed over minus 2, but 6 divided by minus 2 is minus 3, so I get minus 3t cubed. So This is why I like doing it the multiplication way rather than the division way, which is the same thing, but it makes it nice and easy when your dx by dt is a fraction. You can just flip it easily. Could anyone suggest why h provides an added level of difficulty? What am I going to have to use, Grace, to differentiate this? It's a product rule question, yeah. So this is Windows. So to get dx by dt, I'm going to have to do the product rule. Do you remember that? Differentiate that, and then it's those two things added to those two things. That gives me my dx by dt. No such difficulty with dy by dt, but that will make that easier. And similarly with f, which is the next one I'd like us to try, f is going to use the quotient rule. You don't need to use the quotient rule for both, because this one you can write as 2t minus 1 to the power of minus 1. So you don't need with that one to use the quotient rule. You can just differentiate it using the brackets method, but this one you do need to use the quotient rule, which remember is very similar to the product rule and is on the formula sheet. So, okay, here's the next one. What I'm going to do after that. The only difference between the product rule and the quotient rule, there are two differences. It's a minus rather than plus, and you're dividing by v squared. Quotient rule. Differentiate e, it doesn't change. If you're checking answers, don't be too anxious if you don't get exactly what they got, because often these can be written in different ways. So for example, you didn't have to factorise with that one, you could have just left it like that. But it looks a lot nicer like that. So F and then K are the other two to try. When you come to K, all is not lost for differentiating. Have a look at page 6 on the formula sheet. Bottom of page 6 to help you. Did you remember to multiply by what you get when you differentiate the bracket with that one? And then it's very sensible, you'll see why in a minute, to write that like that. When the minus 2 isn't to the power of minus 2, so that stays on top of the fraction, but the bracket drops below. Minus 2 means 1 over squared. With my use of the quotient rule, so I've got this times this minus this times this divided by that squared. Is there any value in multiplying any of this out? Well, my advice would be sort out the numerator, leave the denominator. Some of you will spot why I can afford to leave the denominator, what is about to happen, but the numerator I'm going to multiply out, so I've got 2t times 2t, 2t times minus 1, minus 2t squared. So actually it simplifies to, I'm going to go up here, to 2t squared, 4t squared, take away 2t squared, minus 2t. And I can go even further than that, can't I? Because I could write it like that. Again, some of you will understand why I'm bothering to do that, but you know, I haven't touched the denominator, but I think there is value in getting the numerator as simple and as factorised as I can. and I've run out of space here, so I'm going to do my dy by dx over here. And this is a really important step. So dy by dx, I've got this. That's t minus 1. I'm going to rewrite that. Over 2t minus 1 squared. And I'm going to multiply that by this flipped over, which is why it made a lot of sense to change it from that into that. So that flipped over is going to be and I can take out my favourite pen, which is my cancelling pen, because if I were to multiply all that out, this and this would cancel, wouldn't it? So I can do that now, cross cancel. And also I can divide by 2. Remember, this is one term all being multiplied, so I can divide there and there. That would give me a minus 1. So what I'm left with is not much. I've got t times t minus 1 over minus 1, which I would write like this, although I note that in the book they multiply that by minus 1 to make t times 1 minus t. It's the same thing. It's the same thing. So forgive me for sort of labouring this, but there's quite a lot of value in making sure that you're with me. Dx by dt, which is the one we flip, it's always better if we can write it as a fraction. When I'm using the quotient rule, it makes sense to leave, often makes sense to leave the denominator unexpanded, but the numerator, there's value in doing that. And then don't forget the potential for cancelling at the end. Let me just, I'm going to just do, I know it's a lot of me talking, let's just do that last one that I recommended, K. And can I get you to turn to page 6 in your formula books? And I've got a couple spare.
You've got it.
I think I've got some spare copies of that page actually. So right at the bottom of that page, we're told, page 6, we're told how to differentiate some things. Now I know that I can use the quotient rule to differentiate sec, because I can just write sec as 1 over cos. I can even use brackets by writing it as cos t to the power of minus 1. So I could use the quotient rule to differentiate that. And I could also use the quotient rule to differentiate tan, because I know it's sine t over cos t. But we don't need to, because we're given how to differentiate both of those things on the formula sheet. So sec t, when I differentiate it, well, they rather unhelpfully on the formula sheet tell me how to differentiate sec of kx, or kt in this case. But that's all right, k is just going to be equal to 1. So sec becomes sec x tan x. And we actually did that, we derived that using the quotient rule last week. And y is tan t, which we know is sec squared t. Sorry, that should be t, not x. I'm going to do something else here though, because eventually I'm going to have to substitute a value into this. I'm going to end up with an expression for dy by dx, and I'm going to have to substitute a value in, and there's no sec button on my calculator, so that's going to cause a problem. So I'm going to rewrite that. Sec is 1 over cos. And it might make sense to write tan as sine over cos, although I do have a tan button. So hopefully you can see that that becomes sine t over cos squared t. And sec squared is 1 over cos squared t. So you just want to see if you can finish that one off and tell me what dy by dx is in that case. So I've differentiated x using the formula sheet, differentiated y using the formula sheet. I've now got to combine those two answers. So dy by dt and dx by dt flipped over, dt by dx. And out with a cancelling pen, I get 1 over sine t, which is what I'd use if I was substituting values in, although I note that in the answer they actually write that as cosec t, because 1 over sine is cosec. But if I was going to substitute a value of t in, I'd leave it like that. So I sort of feel a little bit justified in racing through all the other differentiation stuff that we had to do, because within this lesson we've differentiated products, quotients, brackets, e's, haven't done any logs actually, and we've done a little bit of trig, although actually we've used the formula sheet rather than using our sort of sine becomes cos type thing. So it's good that we're practicing all the way through. So let's now substitute some values in. So have a go at this one. So you've got a triggy one and a non-triggy one, and in both cases a value of t to substitute in and a tangent to find. For these you will have to remember that sine becomes cos, cos becomes sine, sorry, cos becomes minus sine becomes minus cos, minus cos becomes sine. We'll again assume, well, it's fairly obvious because t is pi, but make sure you're in radians. need a point as well to work out the equation of the tangent. So for that, you substitute your value of t into the original x and y equations. Did you spot that's a product? If it's 2 cos t, it's not. A number, a coefficient, don't require the product rule. It still works, but you don't need it. But if it's a variable like t, in that case, you've got a product rule out. I could simplify that, but actually all I'm going to do now is make t equal pi to get the gradient. And can I urge you to, when you do that, use the substitution function on the calculator? I mean, actually pi is not too hard, I suppose. You can type pi as easy as you can type x, but I think it's much easier with more complicated substitutions to set your value of x, in this case t, and you'll notice that the x button actually says x theta t, so I'm going to make pi my x value, or t value, I'm just type it as x, and I'm just going to type in, making sure I'm in radians, cos of x minus x sine x, and it will do it for me. And while I'm there, with pi as my value of x, I can work out my coordinate, because to work out the coordinate, I've got to substitute that value of t into the original function. So if I type that into, I may replace the x equals 3 minus 2 sine t, turn that into 3 minus 2 sine pi. That gives me my coordinate, x coordinate. And if I do the same with the y value, so that's x cos x, t cos t, minus pi. So I've got a gradient of -1/2 and a point of 3 minus pi. So we're hopefully able to work out the equation of the tangent using our normal y equals mx plus c approach. So I get a pretty grim value of c, and if you wrote it as minus pi plus 3/2, same thing, same thing. Please ask for help if that's not clear, and then have a go at part B, and then we're going to just trog through. We won't have time for much more this lesson, but that's where we're heading next lesson, 4, 7 and 8. Part B is a little bit more straightforward because there's no tree, so it's a bit nicer without a tree. Yeah, they don't. If you're looking in the answers, don't forget that there's always lots of different ways to write the same equation. So that's what I got, which is correct. They doubled everything. They didn't ask for it in a particular form, so this is perfectly okay. So with that second one, gradient did the differentiating. It didn't really need to do the factorising. I don't know. Just you still get, because all we're going to do is substitute the value of t in. Needed the point, so I used the t value in the x equals and the y equals equation to get that point, and then it all fell out nicely.